Okay, so we're looking at PID systems to closed loop control. And so last week we just did proportional control. And today we're going to go ahead and look at a closed loop control or with either a PI or a PID controller. So this is just some general stuff, but here is the block diagram kind of showing the PID controller. So if you remember here, we have the system that you're going to control is over on the right, and it's outputting some output. And so in this graph, that's what they're calling Y of t. So Y of t is the output that you're going to try to control. And on the left side, you've got the set point. Okay, so Y of t is over here. This is what we're trying to control. And over here is the set point, which is where we want it to stay at. And so we have this feedback coming over here into this summing junction. So remember, this is referred to as a summing junction, but it's negative feedback. Okay, so this is negative feedback. And so this is generating an error signal then. Okay, so the error is the difference between the set point where we want to be and the actual output where we actually are. All right, so last week we were doing proportional control. Proportional control here is where you just have some gain that you are multiplying times this error. Okay, and so that was our just our closed loop control last week. We're just multiplying this gain. So we have some gain, what they basically have labeled as K of I right now, times the error signal. And then that then was what we were sending out as U of t. U of t, what they're showing as U of t down here is our actual control signal into the system that we want to control. Okay. All right, so as we saw with that last week, the problem with proportional control is it'll speed up your system, but in general, it actually causes the system to have more steady state error unless you really push the gain up really high. If you push the gain up high, then you can kind of you can tend to drive the steady state error smaller, but in reality, you're never going to get the steady state error to zero with just simply proportional control. Okay. So so what we can do then is we can add integral control. And basically what integral control does is it integrates the error. So it keeps adding the error. So if there's any error, we add and add and add the error so the integral keeps adding the error up so that it's going up and up and up. And that basically, it's accumulating this error. So the first time around the loop, right? So as you're going through the control loop, the first time you may have a little bit of error there, maybe you have a whole bunch. But what happens is with a proportional control, it doesn't have enough to push the system. And so what you do is with an integrator is you remember how much error you had last time. And then you add that to the new error. So the next time you go around, you add this you add this error up again, and then you add it again, and you add it again, and you add it again. And so finally what happens is your value gets so big, this value here gets so big that you can, you basically just keep pushing the system and pushing the system and pushing the system until you drive that error to zero. So effectively what the integral control is going to eventually do is drive the error to zero. All right, now it may not be able to do that because it may not be able to push the system hard enough. All right, and I was thinking about adding this to the slides, but I never got around to it. But if you take like an example of, say, like you know, like a big sports car, like you know, like a Trans Am or something like that, or Corvette or something, and then you compare that to like a Chevy Chevette. I don't know if you guys know what a Chevette is, but I was going to grab a couple of images on this just to try to give this to you, but okay. So here's 1985 Chevette. Let's look. I just want an image of it. Okay. So here's this Chevette. Okay. And so Ron remembers the old Chevettes. Okay. So you got this Chevette here, and then over here we got a Corvette. Okay. And you know, so we have some Corvette here. So like when you're trying to push the speed envelope, if you will, right? You want to go faster and faster. You know, with a Corvette, obviously, you know, you can, you know, for $60,000 here, you know, you can probably go pretty fast. But with a Chevette, you know, you were lucky to break 60 with a Chevette. Okay, so you know, it was just you just couldn't go too much with these. They just had this little what I kind of think sometimes as a rubber band engine or something, and so you just, you know, if you got this Chevette, you're just not going to go much. But you know, and so the thing is, when we're talking about control systems, you're limited to how much you can actually push the system that you're trying to push. Okay, and so you know, you have maximum limits there, and so that's kind of like, you know, so you may not be able to drive the error to zero because you can't push it that hard, right? So it's kind of like trying to get that Chevette to go, you know, 80 mile an hour or 90 mile an hour. Yeah, you know, good luck doing that. But, you know, with a Corvette, on the other hand, you're not going to have any problem pushing it to, you know, 80, 90, 100 mile an hour. Okay. So, so that's kind of an idea here, is that, you know, you got to keep in mind that we're building this control system, and we're building the control system inside the PLC. And so the PLC, maybe when it can calculates how much do I have to push it, it's like, hey, you got to push it like you're driving a Corvette. The problem is that we actually are driving the system with a Chevette instead of a Corvette, and so we can't push it that hard. So the control system's like, whoa, we would go, and in reality, we can't push it that hard. All right, but the idea is, if we can push it hard enough, we can eventually keep adding these errors up, and add them up and add them up until the error goes to zero. So then when the error is zero, then it just stays steady. It doesn't move anymore. All right, so that's kind of the idea for the integral. And then the derivative, there's this derivative piece here. And the idea of the derivative is that what we're doing is we're looking at the change, Okay, this is dE over dt. This is looking at the change in the system. How fast did the system change? And so if the system is changing really, really fast, then we're going to use that to kind of generate a control response. Okay, if the system is changing really slow, then this number is going to be very small, and therefore the derivative piece isn't going to do very much. But if the system is bouncing all around, and as it's changing really fast, then with the derivative piece, what we're going to do is this scaling factor here is going to be really big. All right. And so the derivative piece is kind of used to respond to very quick changes. And so you want to, a lot of times with the derivative piece, you actually want to use it to slow the system down. Okay. So if the system is changing very, very fast, then the derivative piece will get very large, and the idea is for that to kind of maybe slow down the system. Now, with any of these controls here, you're using these gains. So you have here, you have a KI or a KP. Yeah, it's KP. It just looked like an I when I. So you have KP, which is the proportional control. And then you have KI, which is the integral control gain. These are gains. These K's here in this thing are gain factors that we get to choose. And then we have a gain for the derivative piece. And so we get to pick these gains, and that's referred to as tuning. Okay, so choosing what value of gain you use for each of these is referred to as tuning the controller. And that's really the trick to PID controllers, is tuning them and picking these gains in such a way that you get the response that you want. So that's kind of the thing. If you increase the proportional gain, then you're just increasing your response to the error. All right. If you increase the KI term, then you're basically increasing your reaction to the summation of error over time. And so as the error gets larger and larger, then you're increasing that because you're adding that all up. This is that summation term. And if you increase the gain for your derivative piece, then what you're saying is that when you have a very quick change, you're going to do something drastic. Okay. And sometimes you may even want to make this a negative value to subtract it. Okay. So, but those are our three gains that we have that we can use to tune the system. All right, so just kind of going through the slides, the rest of the slides here, and you guys can read through these, okay? But as I mentioned, the proportional depends on the present error, and so it's going to respond to the error at this instant, okay? The integral is accumulating of all your past errors, and so as your error, if your past errors are all zero, so you're right where you want to be, then the integral isn't doing anything because you're where you want to be. But if you're not where you want to be, it looks at that and it remembers, hey, I wasn't there last time, I'm not there now, and I haven't been there for 10 minutes, and it keeps adding that up. And then the derivative is trying to predict how fast we're changing. So they're like here, they're saying future errors. Well, how are we predicting future errors? We're predicting future errors by trying to determine how fast we're actually changing now. Okay. All right. So, and then for our actual control then, our actual control is going to be the summation of the proportional control value plus the integral control value plus the derivative piece. Now, a lot of times people only do a PI controller because when you do a PID, it's really easy to drive the system out of control. Okay. And so, you know, to get the system out of control, it starts bouncing around. It's not behaving the way you want. I think I've pretty much already said all this. Okay. So here, further down in the slides, I give you some examples where I'm changing just one gain. So this is an example of a system kind of like our LRC circuit that we have. And we, for this example, our steady state error is 0. So they're all going over here to the final value. Okay. But what I'm doing is I'm changing the proportional gain. And as I change it, as I make it bigger, you can see, so with a K of 0.5, that was this red line. It was really, really slow. With a K of 1.1, I speed it up. I get just a little bit of overshoot, kind of dip back below again, and then I reach my final value. And with a higher gain, in this case, a gain of 1.6, I actually have a lot of overshoot. I'm bouncing around for a while before I finally settle down to my final value. Okay, so that was adjusting just the proportional gain. With the integral piece here, what we have to do is we have to deal with this thing called delta t. So if you remember, we talked about, I don't know if I have the slides in here. I should have. We talked about integrators right after spring break. Okay. And so the idea with an integrator, I'm going to kind of try to sketch it here. Actually, let me open up Paint and sketch it with Paint. All right. So you might have some system here. That kind of looks like this. I'm just kind of trying to get a system kind of started here. All right, so here is my system. And this is versus time. Okay, and so over here is like some kind of magnitude of the system. Okay, this is my process variable that's changing. Okay, and so what I want to do then is I'm going to look at this at various points in time. And these various points in time here should all be constant, okay? And so this is this time here is what we call delta t, okay, which is the change in time for each one of these squares, okay? So if you look here, all right, the time from here to here is my delta t, okay? And ideally, this is the exact same time, whatever this time here is, that's the exact same time here, and that's the exact same time here. So what we're going to do then is we're going to calculate at least an approximate error by looking at the height of these values. Okay, so we basically have a trapezoid here. Okay, so this is a trap 1. Okay, so these trapezoids here, all right, the area of TR1 is the height 1 Okay, so we're looking kind of at these points here. Okay, so at this point right here, and then at this point right here, and then at this point right here. Okay, so we have these points, point 1, point 2, and point 3. So the area of TR1 is, it's a trapezoid. So it's 0.2 plus 0.1 okay, divided by divided by 2 times this delta t, which is the time. So this is our change. This is the area. This is how we calculate the area right here. Okay, the area of this trapezoid. That's the calculation for it. Okay, it's 1/2 height 1 plus height 2 times the base. Okay, and the area of this other one over here, the area of this other one, area of trapezoid 2, is 0.3 minus 0.2 divided by, let me actually just draw it underneath there maybe. All right, so it's divided by 2 times the delta t. Okay, so maybe you can see it a little bit better there. All right, so these are your areas. All right, so this is the area for this trapezoid. And this is the area for this trapezoid. And what we're going to do is we got to calculate these areas and add them together. Okay. But we need to do this with such an equation such that the equation is constantly being updated. Okay. And so the way we do that is we have to see, if you look at this point right here, right? Point, if you do the first rectangle, this one over here, okay? All right, so if you look at this one over here, okay, we used 0.2 and 0.1, okay? But now when we come to this rectangle here, we used 0.3 and 0.2. Okay, that should have been a plus there. Sorry about that. That should be a plus. Okay, but so you notice what happened is this, as we're moving along, let me pull these out here for a minute again. Okay, so as we're moving along, when we do the first rectangle, we have 0.1 is here, and then we have 0.2 is here. But now, when we do the calculation again, basically what's happening is 0.2 is here and 0.1 is here. So what happens is what was 0.2, right? So this guy right here was 0.2, but now this guy is 0.2, and 0.1 is what 0.2 was used to be, what 0.2 used to be. All right, so what we have to do is we have to move. So before we calculate the new 0.2, we have to move 0.2 to 0.1, so that every time you're really just calculating with 2 points, 0.2 and 0.1. But as you move along and you go to your next rectangle over here, so if you come over here and you want to do another rectangle, okay, so if we're going to do this, whoops, can't do that one. We're going to go to this rectangle, then the 0.2 is moving, okay, but it's, I can't calculate the new 0.2 yet. Okay, so what I got to do is I got to kind of take this 0.2 and shove my 0.2 into 0.1 and then calculate the new 0.2. Okay, so we have to basically do a move, which is going to move 0.2 into 0.1, and then we can calculate the new 0.2. So you have to continuously keep moving and moving and moving that along. Okay. All right, and like I said, we talked about this before, but I thought I'd kind of rehash it here. Okay. All right, so now, I don't know if it'll let me go back anymore. All right, but for derivatives, we kind of have the same thing for derivatives, okay? But with derivatives, the equation, all we're doing is we're calculating how fast this thing, so we're looking at the slope. So if you go back and you think about the slope equation when we were doing scaling, okay, the slope equation is 0.2 minus 0.1 divided by the time. Okay, and the time is simply this delta t, whatever delta t is. Okay, so whatever the time is, you're just dividing by that time. Okay, and that gives you your derivative, and then we're going to multiply it times our proportionality piece, our tuning game. Question? Somebody have a question there? Okay, so anyhow, so that's kind of what we have to calculate inside of the PLC. And so if we look here, as we do this calculation for the integral, okay, see that, remember, we're actually, we're calculating, we're multiplying like times the error, okay? And so we go back to this diagram here, right? What those equations I was giving you was calculating the error times delta t, okay? And then here it's error divided by delta t. Yeah, I'm sorry. Yeah, I guess when I was doing that, I was dividing by delta t for my integral. I should be multiplying. Okay, should have looked back there. So sorry about that. But and then we have these gains that we're going to multiply, which we get to pick and to give it our nice response. All right. So if we look here for the integral. Thought I had a plot showing just changes in the integral. Well, this is a derivative plot here. Okay, so here's the plot of the derivative. And so you see, again, the final value, the derivative will not affect your final value at all. Okay, so the derivative will not affect it. But what will happen is you can use the derivative to kind of slow down the response. Okay, so the idea of the derivative again is you're looking at how fast is it changing, and it's changing really, really fast. But if we increase our gain on our derivative, then maybe we can slow down the system some. Okay, so we use the derivative piece to kind of slow down the system. All right, so and then again, we put it all together to try to control the circuit. All right, so for today's lab, all right, so for today's lab, what we're going to do is I've got two systems for you. This is last week's lab here. Sorry. So if we go to lessons, okay, today's lab might help if I get in the right class. All right, so today's lab here is to use the simulator. So what I've got here is I've got a couple of different programs. I've got one which is called RLC System 7 Fast, and then the other one is RLC System 7 Slow. Now both of these have a steady state error, but the slow system is really the same system you guys had last week. I made a couple of adjustments to it because I had a couple things in the wrong place, and I just kind of tweaked a couple of things, but it's basically the same system you had last week. All right, but the fast system, let me show you the fast system here. Okay, so here is the fast system. And so if we go to X4, you see it bouncing over here? Okay, there's ringing in here. So this system is like really, really fast. Okay, and so what we want to try to do with this system, at least part of what we want to do, let's look at the trend here. Okay, and so you can see here, you see all this ringing going on here. Okay, and if we hit our history and we zoom in on this a little bit, I didn't let it run very long. All right, but you can see that this is bouncing all around. Okay, that's that ringing. Okay, so you can see it just bouncing quite a bit here as we look at this system. Okay, so you can just see it just bounce, 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 bounce. So this is a really, really fast system here. So we want to try to slow down the system. So you can see it here. You see these numbers bounce over here, or if we look at the simulator window, right, you can kind of see it bounce when it jumps up and down. It goes real high, and then it kind of looks like a springing action there, right? And so what we want to do is I wanted to give you kind of a different system. So we've got the slow system, which, like I say, it's really identical to the system we had last week. And then we have this newer system. So what we're going to do is for both of these systems in the lab, you're going to build a PI controller. So we won't mess with the PID, and then also a PID controller, and just try to get a nice response out of them with just a little bit of overshoot, but not too much. So if we go back and look at my, all right, so if we come back up here, what you want to try to do is to get something like this one, this black trace here, or maybe the green trace is okay. All right. Or even the red trace, right, where you get just a little bit of overshoot and then maybe bounce back and then come and just settle down. Because like right now, that fast system is doing this. I can't draw it very well, but it's like, all right. So it's bouncing all around. And so what we want to do is we want to try to get it a lot more controlled. It's okay to have a little bit of overshoot. Okay. Or, you know, you might just have a slower system with it. But I'm asking, you know, really with that bouncy system especially, you want to have a little bit of overshoot in there if you can get it. But the idea is to just tune these controllers to get them to where you want them to be. Okay, so let's take a look over here. What we got to do is hit it twice there. All right, so what we're going to have to do is I already give you a delta T. Okay, so you already have a delta T timer. All right, and so we have the set point where, oh, I'm sorry, okay, go to the main. If we go to the main rung here, okay, we have a delta T timer. So here's my timer. It's actually called delta T system. Okay, is my timer. That's the timer. And so delta T is whatever the preset is. So for this system, it's 5 milliseconds. Okay. And so then what we need to do, here's our open loop that we had before, rung 8, which was just sending the set point out through the control, right? That's our open loop. And so what we need to do is before the system, we need to insert a rung, and we have to remember we have to deal with these 0.1 and 0.2, which are actually going to be our errors. Okay, and so what we're going to have to do is when we go to the next value, 0.1 moves up where 0.2 was, and then we find the new 0.2. All right. And so, but you have to move the 0.1 first. Okay? And so when you look at the code here, what I've got is I've got a move statement, which is moving my error to a value I called error previous. I mean, you could, I could have called this 0.2, and I'm going to move 0.2 to 0.1. But notice that I only do it. Notice the done statement here. I only do it when delta t is done. And then I also only do it when I turn on the X2 control button. Okay. So this is when I am doing it. So the first thing I have to do is I have to do the move. Then I'm going to calculate the new error. The error is simply the set point minus the RLC, which is our feedback, our Y value. Okay. And then I threw in this calculation here because I need to get the delta t. Now, I hard-coded delta t up here to be 5 milliseconds. Okay, but if you change it, if you decide to change your delta t, then you need to use the value you calculated. So, and actually for this, you probably shouldn't, seeing as how the system's being simulated. And it'll mess up the simulation system if you change delta t, because the system I'm simulating is tied to whatever delta t is. Okay, so don't change delta t. But what I'm doing here is I'm taking delta t. Okay, so we've got here delta t times the accumulator divided by 1,000, because the accumulator is actually going to be like 500 or whatever, right? So I've got to divide it. Okay, at least okay. And then here is my control expression then. All right, and so what I've got here is I've got R1. This is my error. Well, this is my gain. WX1 is the gain. I say that in the lab. WX1 is your gain, which is this is an analog input. So we can tune it. We can adjust these on the fly. Okay. So I'm using analog input 1 is my proportional gain. Analog input 2 is my integral gain. And then when we do derivative, we'll have that. But this is R1 times R2, or plus R1 plus R2, those are my points, times my delta t, okay, divided by, and what I'm doing is I'm dividing this by 1,000, because remember, this is an analog input. The analog input goes anywhere from 0 to 4,096. And so I'm dividing it by 1,000, which means that my gain can go between like 0 and 4. Okay. And if you need more gains, you can divide by 500. Okay. But then here I've got a factor of 2. The 2 comes from the trapezoid rule. So remember that a trapezoid is 1/2 times the base times height 1 plus height 2. That's the area of this trapezoid. All right. And so that's what I'm doing over here. I've got my two heights, which are real values, R1 and R2, times delta t. Okay. And then I'm going to divide by 2. So that's my 1/2. I'm going to divide by 2. But I'm also going to divide by I'm also dividing by 1,000, because WX2 is from 0 to 4,000. If I give it a gain of 4,000, the system's going to blow up. Okay. All right. So when I press X2, I'm going to calculate control output. And so now if I run this simulation, and I increase these gains, okay, then I should be able to drive my system. Okay, now right there it's out of control. Okay, so you see that just bouncing around like that. It's just the gains are way, way too high. Okay, I may also have a calculation error somewhere. I may have to go back and double check my calculation. All right, but well, when you drive this system here, okay, it should be driving the error to 0, and it's not. I'm not quite sure why. Doesn't seem to be wanting to go to 0. Let's look at a trend here. And so all right, I also want to choose, I think it's this one. I forget. I wish it would give you the labels. I labeled all these, but it doesn't. There we go. All right, so it is not driving my values. I might have a sign error or something in here. I'm not sure. Okay, but what you're doing is you're taking your error and applying it. That's your proportional control. Okay, so this amount here is your proportional control, and then you're adding your integral control. Oh, I know what I'm not calculating. This is not actually integral control here. This is because I'm not adding it to the previous one. So what I need to do is I need to add another calculation here. Okay, so I need to keep adding in my previous integral values. So I have to add up my error. The one in Blackboard, this is the control. This is where you need to end. Yeah, yes, that's correct, Matt. This is your control that you've got to add in here. Okay, so the one in Blackboard doesn't have this because the one in Blackboard is just open loop system. And then you have to add your control. That's your lab. Okay. All right, so but what I'm missing here is I need to continue adding the error up. So actually I put this other lab in here because I had the equations in the other lab. So if we go to here, if you look at this one I call reference, I have the equations in here for you. Okay. And I was trying to get this done before class and I was in a hurry and I didn't get it quite working yet, but I have the equations are in this lab for you. So notice here I put in big words. This is just your reference lab. This is the lab we would be doing if we were in the classroom. All right, but since we're not in the classroom, this isn't quite correct. But here is all your equations. Okay, so you've got to create compute statements for these. Okay, and then you calculate your control out here. Okay, that's not what I have in the lab right now. I was trying to get it working before class, but I only had a little bit of time and I obviously did not get it to work. So I'm going to leave that for you guys. Okay. And so I'll go back and work on mine too here. But if you look at this lab that says reference lab, I give you all the equations. So you have to build compute statements to do these calculations. Okay. Oh, and this delta t, that I think I'm missing that too because I need to divide by 1,000 the reason I'm dividing by 1,000 is because delta t is in milliseconds. Okay, and so you need to divide by 1,000 to get seconds, which is probably why my system is blowing up. Because delta t, I'm multiplying times delta t accumulator value, which is probably a really big number. I wasn't looking at that number, but that number is probably really, really big. Let's look at that on my simulator, because I probably need to divide by that. So if I come over here, I really like this data section here. So you can actually put delta t here. Okay, and this delta t, did I divide? I think no, I did divide that. Let's see what that value is. Okay. So delta t, okay, delta t is 0.05. So that delta t is correct. Because it needs to be in however many seconds, it needs to be in seconds, but that is in seconds. Okay. Because if we look at the delta t system accumulator, okay. So I guess the way they're showing it is just in seconds here, but okay. So, but the delta t is in milliseconds, and so it's 5 milliseconds. Okay. So 0.005, that is correct delta t. Okay, and that's what this one over here is doing, is that piece. So you may have to create a few more compute statements to calculate this. All right, but I give you all the equations here. This is the proportional control. This is the integral control. Okay, and then this is the derivative. And so you definitely want to kind of read through this lab as far as calculating your integral control signal, because that value needs to keep adding up. All right, so, but I'm giving you the equations here in the lab, and in this reference lab, so, because I didn't have a chance to get them entered into the other lab. Okay, but what we're going to do is we're going to use, and I would recommend you start with the slow system, okay, because it's the slow systems are easy to work with because they don't blow up so quick. You know, this fast system, it's really bouncing around as it is, so it's going to be very touchy to try to get the gains correct, because if you get too big of gains, then even with a derivative gain, you know, if you make that derivative gain too big, instead of it trying to settle the system down, sometimes it'll actually drive the system unstable. Okay, so you need to but the idea here is that when in your simulation now, you can adjust these gains. So this is going to be your proportional gain. This is your derivative or your integral gain. And W3 is your derivative gain, which I don't even have in there yet. And so when you get these correct, you should be able to get the system to track your input and behave fairly decently. Maybe a little bit overshoot's okay, but you know, it shouldn't be bouncing around. If it's bouncing around like right now it is, okay, it's not unstable, but it's bouncing a lot. Not quite sure why. I think I'm missing a part in my integral piece because, see, that's actually, it's kind of tracking, but it does have a lot of steady state error. And the reason it's got all that steady state error is that my integral piece isn't remembering that error. So I need another compute statement in there because I got to keep remembering that. So let me go to Paint once and try to write it out here. You need to take the error. So you're going to have, like, this is going to be your error at this time, error 1. And then this is going to be error 2. And then this is going to be error 3, and so on. And so what you have to do is you have to take your error, okay, your error previous has to equal your error now plus your error previous. And I forgot this piece, error previous. Okay, I don't have this equation in mind, so it's because you need to be adding this up. So it adds and adds and adds so that it, as I said before, it's going to like grow and grow and grow. So it's like here, and it keeps growing and growing and growing and growing until it drives that system. So if we okay, so here we have the open loop system that this is the fast system for the lab. And as you can see, right, as we change from set point, a high set point to a low set point, we get a lot of ringing going on. So you can see it's peaking up here somewhere above 3,500 when the set point jumps up to 2,500. But then it does settle rather quickly. Okay, so this is the open loop. So what I've got here is the PLD closed loop control system here. So this rung here does the calculation. So the first thing we have to do is we have to move the error into the previous error so that we can track those to calculate the area for the integration. Then the next thing we're doing is we're calculating the actual error. So we move the error into the previous error, and then we can calculate the new error, which will give it, which is calculated by set point minus the process variable, which in our case is RLCK, the essentially the voltage across the capacitor. Next, we have the delta T calculation. In this case, I've got delta T is my timer that I'm using for the calculations here. And so there's delta T, and you can see it's just set to 5 milliseconds. All right, so in this case, I've just am hard coding a variable delta T to be 0.005. And then we calculate the integration then. The integration is the trapezoid, where we have the error plus the previous error times the delta T divided by 2 plus the previous calculation, because remember, we're integrating here. So we continue adding and adding. So the error will grow and grow. And then we're calculating the derivative. The derivative is the difference between the current error and the previous error. And then I'm multiplying it times 1.0 just to make sure that it's a floating point. And then I'm dividing by delta T. So we have the change in the Y divided by the change in the X. And so that gives us our CO underscore derivative piece. Then to tune this, I'm using wx1, which is the integral um, analog input 1, analog input 2, analog input 3. Okay, and so I'm using each one of these to scale the input. And so remember that the analog inputs go anywhere between 0 to 4096. And then what I'm doing is for the proportional value, I'm going to divide that by 2000. So really the max that I could possibly get out of that would be about 2. And the same for the gain for the integrator piece. So wx2 divided by 2000. For the derivative piece, you have to be very careful with your derivative that you don't get too big of a gain, because remember, the derivative is reacting to a change in the system. So if the system is going to change very quickly, then the derivative term is going to be very high anyhow. So you don't want to multiply that times a huge gain. It's very easy to knock the system out. So in that case, I'm using the third analog input, but I'm dividing it by 8,000. So the highest possible derivative I could get out of that, or gain I could get out of that, would be about 0.5. Okay, and then I'm calculating the error, or I'm calculating the control based on the k proportional times the error plus k integrator times the control integrator calculated above, and then k derivative times the derivative piece calculated above. Now remember, we're only calculating a new CO integrator and a CO derivative when the timer is done. However, we can still output, we're still outputting that value for every scan cycle. So for every scan cycle, we are going to output a new control, and that new control is the proportional times the error, which this value is changing every single time, and then the integrator times the previous integrated value, and then the derivative times the gain of the derivative times the derivative calculated value at the last delta t. Okay, so we're outputting a control every scan, but this control, the k proportional times the error, that is changing every scan because the error might be changing, and but the CO integrator and CO derivative are only changing every 5 milliseconds when the delta t expires. All right, so when we look over here in the data column, I've got some values here. I've got the set point, so we can see the set point is changing between 750 and then stepping up to 2500, and then it steps back down to 2500. And so you see it just changed down to 750, and then it's going down. And so right now we just have the open loop. Okay, so the simulator is running an open loop. So we see that it's got X4, and all X4 is doing is outputting the set point to be the control out. Okay, so this is open loop. So the set point is just hard set to the output. And so it's just 2500. And so when we look at the trend here, we can see that ringing, right? It steps up to 25, set point steps up to 2500, and then we get some ringing, and then we have this steady state error. So you can see there's significant steady state error, and then it starts ringing, steps down, it's ringing, and then there's still some error there. The error is not quite as large for the 750 set point, but there's still quite a bit of error there. All right. So, and you can see the control over here. You can see that the control is just following the set point because it's open loop. You can also see here's my current gains. Now we're not using these right now because we're running open loop, but when I switch it to closed loop, these are the gains that I currently have set. So I've got a proportional gain of about a little over 0.5. I've got an integrator gain of a little over 0.6. And I've got my derivative piece. Remember, this derivative piece I was dividing by 8,000. And so my derivative term is actually just very, very tiny here. It's 0.000, that's 3 zeros, and then 75. So it's a very, very small gain. Now these are just gains. These are unitless gains, so they don't have like a voltage or anything of that nature with them. Okay, and then there's just my delta t, and this is just my delta t timer accumulating. You can see it accumulating up to 5 seconds there, or 5 milliseconds. And then we have the current error, the previous error, which every time delta t trips, then the previous error will change, but that's only happening when I'm in controlling. So that's why these aren't changing right now, because I'm in open loop. But when I go to closed loop, you'll see that those will change. Okay, and then you see the integrator values. Again, these last 4 values down here are only going to change when delta t is done, when the timer is done, when I'm in control mode. So they're not changing right now because I'm in open loop. So I'm going to come over to my simulator there, and I'm going to take off open loop and close the loop. All right. And so now you can see that these last 4 values over here are changing quite quickly because they're changing every 5 milliseconds. And you can see that we are stepping down. So the green is the control. The red is where we want to be. So you see that we don't have this high ringing. See over here, we have this huge high ringing up here. So we got rid of the high ringing. Now there is a little bit of ringing when it changes here. There's a little bit of ringing because it's a fast system and it's going to bounce around. And so when you give it a drastic change, which a step change like this is, we're just stepping up and stepping down, there is definitely going to be some ringing here. But you can see that we've really cut out that ringing. It's not ringing way up here to 5,000 like it was before, or way above 3,500 anyhow. And then you can see that the red, which is our actual output, is getting real close to that. And if I go ahead then and extend my, let this run a little bit longer before changing the step again. So I'll just adjust that over there. So you can see, watch the clock value. Okay, I'm going to extend it a little bit more. It still didn't have time to reach steady state there. Okay. And so we're at 750, and you can see that our process variable here is dropping down, and it's getting closer and closer, and then it's jumping back up. So you can see it's moving up. I'll go ahead. I've currently got my step changes, my flip-flopping, that happen a little under 20 seconds. I'm going to take it up to about 22.5 seconds, or 25 seconds, a little over 25 seconds. So it'll have plenty of time here. So you can see that it's 2499, and then it changed again. Okay. And so now it's driving it down. The controller is driving it down. And so it's at 750, 77. Now notice the integrator error. So the error is getting less because we're getting closer and closer. Okay. And so now it's not changing anymore because we reached the value. So the error went to 0. Okay. So the error went to 0. So the integrator value wasn't changing. Okay. So you kind of watch here, you see the error and the error previous and the integrator. So the integrator piece is integrating and pushing it higher and higher the error is almost zero now. Error's just about to zero, and then it toggled and it went. So let me extend it another 5 seconds here. All right, so I'm about 30 seconds. And so again, you can see, the set point 750, we're at 752, 751, 750.5. Okay, so the error is 1200 here, the error is very small, and then it jumps back up to 20. So now we're headed back up to 2500. But you see how before it was ringing all the way up here above 3500, and now there's a little bit of ringing right here, but that's it. Okay, and we don't really have any overshoot. Sometimes you'll see that ringing would like overshoot up here into this an over set point, but because our set point is so high, we're not really seeing that ringing, and our controller is just kind of tightening it. But you notice it's a much slower system now, right? It's taking 20 or 30 seconds to get up there to essentially there, but you can also see that the steady state error is being driven to zero. All right, so that is the PID controller. So let's just kind of look at it one more time here, come back to the main. So I basically have it on 2 rungs. So rung 9 is taking the error, moving it to the previous error, and then calculating the new error, which is the set point minus our process variable RLCK. I'm just hard coding the delta T. I could have done that in a different way, but I had it in here. And then we have the integrator is calculating the area under the curve. So we have error plus previous error times delta T divided by 2. That's a trapezoid. That's the area of a trapezoid plus what error we had before. Because remember, the error is continually growing here, okay, or continually decreasing, because we're either adding to it, or if it's a negative error, we're subtracting it, okay? And so you can see here it just changed, right? And the error is getting higher and higher, but it's not changing as fast. As we get closer and closer, the error is increasing, but it's slowing down. So the error is still increasing, but it's slowing down, okay, as we reach that final value, okay? And then the derivative piece, you can see the derivative piece here. When we first make the change, so when it first makes that change, flip back to the trend here and we'll kind of watch when it jumps, okay, it's going to jump here in just a little bit, okay, and when it jumps, you're going to see a high gain. See, the derivative piece is real small now because it's barely changing, okay, so it's like 0.0 something, so it's very small. Now we jumped and it's 300, okay, so during that jump, that derivative jumped up really high, okay. I'm not actually plotting that. If we add that to the trend, we'll see that. Let's come over here to our trend, and I'm just going to go ahead and add the CO derivative piece so we can see that. So that one is this R21, and you can see, right, that you see that cyan color just jumped off the screen here because the change was so drastic, right? So the change was so drastic there, it was bouncing around, and now you can see that the changes dropping to 0. So that derivative piece will spike. So it gives us that quick reaction to kind of to react to the changes. So it goes up and it goes down. So there's some negatives in here too. If I extend my things to a negative minus 500 maybe, and see if that goes negative, okay, when it toggles, because the derivative, because this thing's bouncing, remember it's ringing here, and so the derivative is going positive one time and the next time it might be negative. And so you get this huge bouncing around of the derivative piece. So you see that? That's down here at minus 500. And it's off the chart. So it's probably going even further because it's such a drastic change right here. But then it settles down and it goes to zero. This is zero right here at the crosshairs. Okay. And so that's the derivative piece, and you can see how fast that's changing. Okay. All right, so there is the PID controller.